we have a request to do a roadmap from Fall 19 Test 3, Part 2 continued. And we're supposed to start over here with acetylene again. Yes, that's acetylene. It's been our theme all day. And that's vinyl potassium we just learned. That's the conjugate base of vinyl. So I'll scribble it up there. CH minus with a CH2 goes to HCH2, CH double CH2 with a pKa of what? It's an alkene. It's an alkene. 45. So the alkyne was 25. That's acetylene. pKa equals 25. And the 45 is the alkene, -20.
Where did the one come from in the first one?
What's your alternative? And I'll show you why it's wrong. It's only got one H on it and a potassium, which is a spectator. I just crossed it off. By definition, this is C minus.
Oh, I see what you get.
And there it is up there. And you need a double bond, or else you got octet violations.
Yeah.
All right, so there's your acid base to make the acetylide. That's potassium acetylide, and it's a nucleophile. And these carbons, I thought I had my highlighter. This portion is this portion. The synthesis bond is this bond right here. That's new. So the new group is here. I wanted a new color. It's an isobutyl group, but it has to have a halogen on it or else there's no reaction. Isobutyl. And on this part of this test, you can pick any halogen in the universe. Not fluorine, though. Never pick fluorine. Chlorine, bromine, iodine. Earlier today, we were using chlorine. We can use bromine. There you go. It has to have a halogen on it. For our synthesis steps, you need C minus that comes from an alkyne and a carbon with a halogen on it. So that's it. And then we're doing more synthesis. Do you know how I know that? This H is gone and replaced by a methyl. Just like in this one, this H is gone and replaced by an isobutyl. That's over here. So what did you do first to get rid of the H? Step 1, base. Don't use that KCHCH2. Use our favorite one we've been using all the time. It's just smaller. We like it. Or use this one, KCHCH2. I don't mind. Any of the top 4 bases will work. 2, you need a methyl group on there. Any suggestions? Chloromethyl, sure. Chloromethane if you want to be nomenclature about it.
You could have used BR.
Or BrCH3, anything, chlorine, bromine, iodine.
Okay.
Stick with those. And then it's about making a Z-alkene. How do we do that? I got to put H's on the same side. How did we do that? Oh, I'm winning them over. It took a while. They resisted. BH3. And you didn't like CH3CO2H. You didn't. Can't you go ACOH? Sure. Acetyl with an OH is acetic acid. Yeah. Or H2 with Lindlar's catalyst. Don't forget the H2. It's not part of the catalyst, but it's part of our molecule. All right, and now we're doing hydroboration. If you want to be clever, it's tritioboration, followed by oxidation. And 2 products. that thing we mentioned earlier today, when you have an internal alkyne and you have either the boron reaction or the mercury reaction, you get a 50-50 mix of two ketones. Because there's no way to get an aldehyde when the alkyne's not on the end. So that's the two products, ketone 1, ketone 2. And ketone 1 has it on the second carbon, third, CH2, C with a V. And ketone 2, CH2, then the third carbon, and then a CH2 and a C with a V. There you go. Internal alkynes. Oh, there's tritium. Oh, sneaky teacher. The other carbon in the alkyne got a tritium. Oh. Normally that'd be an H, and that's why I didn't show it. But it's not an H, it's a T. Okay. All right, reagents to make this into an, oh, we don't know what this means. Isohexane al. Yes, she knows what it means. Aldehyde. So I'm going to copy these chemicals because they make aldehydes, but don't use the T. So reagents to make isohexanal are step 1, HB Cia2, and 2, H2O2 KOH. And this is BH3 and acetic acid, but instead of BH, I use BT. And instead of acetic acid, I use DOAC. 2 points.
If I was to put OH minus, would I get the same amount?
Oh yeah, you can do this anytime you want. You can always leave a spectator out and make sure you have the charge though. You can do that anytime.
So this will be cis.
Yeah, you're gonna get a cis alkene, but the fact is, this one actually, the mechanism is fun. I'm just gonna do a abbreviated mechanism. Because here's the deal, everybody. You got a T and B2T, and you attack the B, and the T goes back to the more substituted carbon. Oh. Yes, that's good for alkenes or alkynes. So yeah, it's not, you can't just randomly put the T where you want. And remember, the B gets replaced by a proton, and that's a deuterium. So I'm just gonna do the whole rundown here. So initially you get the T on the more sub and the B on the less sub. And then the protonolysis is with TOAC. 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 And that just does this. And I need this molecule here, HCC. The R is actually just an isobutyl. And you're going to end up with a T and another T. Wait, one was a D. It was DOAC. I put TOAC. D.
So it matters where you put the D or the T.
Yeah, on a terminal alkyne, it does. 1 deuteryl, 2 tritiol.
So the first thing that
Tritio? No, that's not tritio. It's tritio. And does it have names? No, we just have to draw it. Never mind. You're not naming it. Draw that. That's my answer. Can I? We're running out of time, right? Oh, don't ever hit the mouse. Then I hit the mouse. Hit the mouse again. Okay. That looks messy. This goes in the box. fixed them both at the same time.
We get it.
I'm gonna circle it and move it in, lasso it, move it into the box. There you go. Whew. What about to make 5-methyl-hexane-2-one? It's a ketone on a terminal alkyne. What kind of chemicals you talking about now? Mercury,
Sulfate,
yes.
water and H2 with sulfur.
She's got it down. Remember, we started the day, she didn't know it, she's got it now. She knows all 3 parts now. Okay, and then T2 and Lindlar's, there's Lindlar's catalyst. You see it down there? And T means tritium instead of deuterium. So your triple bond, green triple bond is now a double bond. And we got an H on one side and an IBU on the other. IBU. And tritiums. Tritiums. They have to be syn. You have to learn that reaction is a syn reaction. Yeah.
So the reason why down there with the mechanism that you showed down there, the reason why we put the T on the more substituted
Because this would generate a cation and you want it there instead of there, and this traps the cation before you ever see it. So that's why the T has to go on the more substituted carbon. And then the deuterium goes on the less substituted because it replaces the B. That's where that is. And that's that. Good session. Big picture. And see you Monday or Wednesday for more review.
You collect our budget.